Yeah, the sequence version of Bolzano-Weierstrass theorem, that is, given any bounded sequence in Euclidean space, well then that it had a convergent subsequence. And before that, we considered that every subsequence of a convergent sequence is convergent and has the same limit. Now we'll complete that section just by some further properties which will be useful and which we will need later. Now, one question is, we have in a real vector space different operation, addition, inner product, the usual inner product, scalar product, and so on, whether the limits will stay invariant under those operations. Now, for that, let us take two sequences in Euclidean space. And a sequence in R. Now assume that these are all convergent. Xn converges to X, Yn converges to Y, and Cn converges to C for some xy in Rm and C in R. Now what we can do is we can construct out of these sequences a sequence each of whose terms is the sum of the corresponding terms of these sequences. It turns out that this sum sequence is convergent and in fact converges to the sum of the limits. Secondly, we can do the same thing by taking the inner product of the respective terms, corresponding terms in the two sequences. Now this is a sequence in R, and it turns out that this converges to x dot y. We can do the same thing with the scalar product. Now this is a sequence in Rm again, and this will converge to Cx. Finally, let us also consider this is how the algebraic structure of Rm behaves under taking limits, but we also have an order structure, and we can ask actually a similar question about that. Now, if not for the whole sequence, but from some point on, such that for all n beyond this place, xn is less than or equal to yn, then the limits of the two sequences obey the same order relation. Well, here, regarding for convergence and the limit in case of convergence, well, any initial part of the sequence in question, that's irrelevant. You can change that in any way you wish. If the tail after some point stays the same, well, then that does the job. Now, the proof of this, that's left as an exercise to you. And when we consider continuity, which we'll do in 2 weeks, well, these will be read as that addition is a continuous operation, the inner product is a continuous operation, and scalar multiplication is a continuous operation as well. Now, one last simple result which we wish to deal with in this section on sequences, which we will need later, is the following. Now let's start with the sequence in Rm. Well, so each of these exabands is an M vector. Now we can also consider the component sequences, the sequence consisting, say, of the first components of the vectors in this sequence. We can do that for each component. So we will consider then M different sequences in R. Each component sequence is a sequence in R, while the convergence of this vector sequence and the convergence of the component of the components, while which a sequence is in R, they will be closely related. Now, for each I in 1 to M, for each component that is, X and I, the ith component of the vector xn, is a sequence in R. Now let X be a vector in Rm. Or let me write A here, it's better. Now, Xn, this converges to A if and only if for each component the ith component sequence that converges to the ith component of the limit of the vector sequence. And well, you can prove that easily. The proof of this, that's again left as an exercise to you. Now we will make use of sequences in an extensive way, and this section is just about the basic definitions of sequences and a list of basic properties which will be used frequently. So that's how the construction of this section was. Now, so far, we just made some preparatory work. Our main aim, that was, well, to gain tools, powerful tools in optimization. Now we can, the next two sections, the first one will be on compactness, an attribute of sets, and then the section which will follow that will be about continuity of the functions. Well, the conjunction of the two, that will yield us the first basic results concerning optimization. So this is 1.10, I guess. It's about compactness. Now let's consider the following simple framework. Let A be a finite non-empty set. Now assume that this represents the set of all alternatives available to an agent. Well, then we can represent preferences of this agent in question on A via a utility function. That is, let's take U as a function on A to R, a function. Whenever U of X is larger than U of Y, we interpret that X is better for this agent than is Y. But we wish this agent to be able to make a choice, an optimizing choice from cap A. Well, that is, what are the points, the sets in cap A, which maximize this function? That is, we're interested in the existence of maximum of U of A, where U of A, as usual, this stands for the set of all U of X's such that X is in A. But this also, in some cases, may represent a disutility. Members in cap A might be bads rather than goods, so you wish to minimize this utility. Now, min UA, we're interested in the existence of that as well. But if this set is finite and non-empty, these clearly both exist. But this framework is too restrictive. If we restrict ourselves just to finite sets of alternatives, well, we will, for example, exclude, the set of all commodity bundles, if there are L commodities in our L plus, which are affordable by some agent with some budget under certain given prices. Well, these will always be infinite sets rather than finite sets. So the question is, can we extend this finiteness to something more general by possibly also putting some smoothness conditions on U? If U is behaving wildly, very volatile, well, then we cannot guarantee the existence of maximum and minimum. Well, an extension of finiteness such that this property is preserved for functions U with some property, well, that's what we'll do next time. The extension of finiteness, that will be compactness, and the extension of smooth behavior, that will be continuity. Well, then, let us start by defining compactness, verify that our definition actually is an extension of finiteness, then conjoin that with continuity and get some results, some existence results first, and the structure of the sets of maximizers using these two notions. Now, first we need some auxiliary tools in defining compactness. Well, first we need some topological structure. So let X tau be a topological space. Finiteness is an attribute of a set. Then let's take some set in cap X. Now we will first relate families of open sets with cap A in the following way. Now let I be a non-empty set. We will use this as an index set. So a family G of open sets so if G alpha is open, and this family will be non-empty since I is non-empty, is said to be an open covering of A if the open sets in this family cover cap A in the sense that the union of these G alphas that contains A. Well, before proceeding any further, let's see some examples of collections of open sets, which are open coverings of given sets, cap A, in a topological space, and those which are not. Well, since we will use them all later, well, that will actually not be wasting time. Now, first, let's take as our space R2 under its usual metric. Well, if I take, for example, G as the set of all epsilon balls about X with respect to D, such that X is in R2, will this be an open covering of R2 itself? Let us take the set cap A to be R2 again. Well, are these open sets? Yes, every epsilon ball in a metric space is open. So this is a non-empty R2 is non-empty. This is a non-empty collection of open sets. Does the union of these, when X is here, the index set is R2 again, does the union of these epsilon balls, when X ranges over R2, does that contain R2? Well, clearly so. For any X in R2, just consider the epsilon ball about X that contains X. So these are all in tau D, and the union of BD epsilon X when X is in R2, that contains R2. So this is an open covering of R2. But here I have one open set for each X such that X is the center of that. Well, I can do this with less points in the plane in R2 by taking epsilon, say, large enough. Now, for example, if I take this as the set of all one balls, and just if I take as the centers of the balls the so-called lattice points, well, that is, these two components are integers. Mn is in Z cross Z. The question now is, again, whether G prime is an open covering of R2. Well, these are, again, since they are particular epsilon balls about particular points in the plane, each of them is an open set. So this is a non-empty collection of open sets. Now, does that cover the whole of R2 if you take the union of these? Well, if you draw a picture, if these are the lattice points, now, well, I take this, and then I have this, I take this, I have this open ball, this, if I take this, then I have this open ball, and so on. What does this picture tell? Does this cover R2? It seems so, but it needs to be shown, although that's simple. For the first few examples, let's go through that, through the proof of that. Now take any x in R2. Well, I need to show that there is a lattice point, Mn, in Z cross Z, such that x belongs to the one ball about that point. But x1 is a real number. Well, then I can consider the closest integer to that. Well, no matter what integer, well, now there is some integer n such that the distance of x1, the first component of this, is less than or equal to 1/2. Well, if this is just some integer plus 1/2, well, then there are two of them, but there is at least one. Well, if I take the closest integer to x1, then the distance of x1 from n will be this. And there is some n in Z such that the same holds for the distance of x2 from n. So the distance of x1, x2 from Mn, this is the usual distance. Now what will that be? That will be x1 minus m squared plus x2 minus n squared, the square root of that. But this is now less than or equal to 1/4, because this was less than 1/2. And this is less than or equal to 1/4, this, but then this is 2/4. So this is square root of 2/2, which is less than 1. Well, thus, x1, x2, which was x, this belongs to the one ball about Mn, which I have found here. Thus, R2 is contained in the union of these, where Mn we also write for Z cross Z, Z2. Let me write it here. So this is an open covering of R2. Now let's take R2 again, but this time with a different metric. Remember when we considered epsilon balls, we used another metric for R2, which was given by this. Now, for any x in R2, we had x, well, let me put one here. This is not the usual norm anymore, and the norm we used there was just the sum of the absolute values of the two components, x1, x2 of cap x. This is the norm that we know, and let d1 be the metric induced by this norm. Now let me take this same set, but this time not with respect to the usual metric, but with respect to the metric in here. So let's define G double prime as the one balls with respect to the metric D1 about lattice points in the plane. The question again is whether this G double prime with respect to the metric D1 now, whether that's an open covering of R2. What can we tell about these? Will these be open with respect to D1? Well, given any metric M on a set cap X, an epsilon ball about some point with respect to that metric was an open set with respect to that metric. So these are all open balls. Now the question is whether the union of these, when Mn runs over Z2, whether that contains R2. Now you can remember the picture we had. Well, we had the one ball about the origin. Now the picture was this. Now if I take this point, well then I'll have this. If I have this point, then I'll have this. If I have, well, this point, well, if I take this point, then I'll have this. Does this cover the entire R2 if I go like this? What about this point, 1/2, 1/2? To what one ball about what lattice point with respect to D1 will this belong? Now let me take any Mn in Z2 and just consider the distance between this Mn and this point. D1 Mn 1, 2, 1, 2. What's this equal to? It's M minus 1/2 plus N minus 1/2. By definition of this metric. Okay, I take the difference between these. which is m minus 1/2, n minus 1/2. Then I take the norm of that, which is equal to this. What can you tell about this? No matter what integer m you take, m minus 1/2 will be larger than or equal to 1/2. The closest ones to 1/2 are 0 and 1. Well, in that case, you have equality, but m is different than 0 or 1. Well, this will be even larger than 1/2. But the same here. So this will be larger than or equal to 1, and thus 1/2, 1/2 does not belong to the one ball about Mn with respect to D1 for any Mn in Z2. Hence, this is not an open covering of R2 with respect to D1. We always have some topology, or in case of metric spaces, some metric with respect this is an open covering or not. Next, let us consider R2 extreme topologies. Example 2, X, a non-empty set. Now tau 1 to indiscrete topology. If I take some non-empty subset of cap X, can you give me the entire list of open coverings of cap A? Well, since this is non-empty, any open covering of cap A with respect to this topology has to contain cap X. These are the only two. So G equal to phi X and G prime equal to just this set consisting of X are the only open coverings of A. This also is an open covering. Well, this does not add anything, but the union of these are both open, and the union of them is cap X, and that contains A. Now, if you take the discrete topology, which is just 2 to the power X, again, let us take some non-empty subset A of X. Well, if I, for example, take this singleton X's such that X is in A, will that be an open covering of A? Well, everything is open. These are all open sets. But if I just take the union of the singleton sets, well, one for each point in cap A, well, that's so union singleton X's, X in A, this is just A, thus this contains A, so G is an open covering of A. But if I took G prime just consisting of the set A, will this be an open covering? Yes. A is open, everything is open, thus in particular A is open. And while the union of just one set is itself, A contains A, this is G prime is also an open covering. Okay. But here, the idea which we had at the beginning was to extend finiteness. Here, open coverings of set A, well, they might be finite or infinite, so there's nothing about finiteness so far. But now, we can define one more intermediate concept and then compactness. Again, let X tau be a topological space and A a subset in this space. Let G be an open covering of A. Now we'll define the notion of this open covering G having a finite subcovering for A. Well, that is, there should be a non-empty finite subcollection of this such that the union of sets in that subcollection also cover A. They contain A. Now we say that G has a finite subcovering for A if there is some such finite subcovering, which means if there is a finite non-empty subcollection say G1, Gk of G. So this will be a subset of this collection such that union of the G sub i's I from 1 to k contains A. Now, A is set, the set A is set to be compact, of course, with respect to this topology, with respect to tau, if every open covering of A has a finite subcovering for A. Now let's go through a rich sequence of examples, but let's start with this. Well, our aim was to have an extension of the notion of finiteness. Well, if compactness is an extension of the notion of finiteness, then in any topological space, a finite set should be compact. Well, let's see that that's the case. So first, that's a general example that X tau be any topological space and A in X finite. We'll show that then A is compact with respect to tau, no matter what topological space we start with. Now, A is compact. Now let's prove it. Now what shall we do? The definition says every open covering of gap A has a finite subcovering for A. So let's take any open covering G of this and then show that it has a finite subcovering for A. So let G be any open covering of A. Well, we know that A is finite, but there are again two possibilities. Now, A might be the empty set as well, or it might be non-empty and have, well, the empty set has 0 members, and 0 is also a finite number, okay? Now, case 1. A is the empty set. Can we produce a finite subcovering of G for the empty set? We can take, this is by definition a non-empty collection. Take any set in here. Take any G in G and consider the singleton G. This is a subcollection of this, and the union of the sets in here, which is G, just G, but G, no matter what it is, it may even be the empty set, it contains the empty set. Now, G is a finite subcovering of script G for A. So that condition is satisfied when A is empty. Case 2, A is non-empty. How can we proceed here? Now, if I take any X in A, can I find some open set belonging to this collection, script G, which contains X? Yes. The union of the sets in script G, well, that contains A, thus any X in cap A belongs to the union of all open sets in script G, but then, by definition of union, there must exist some open set G, say G sub X, which contains X. There is some G sub X in this open covering with X is in there. Now, set, consider, well, consider this collection. Is this a sub-collection of script G? Yes, for each x in A, G sub x belongs to script G. Is this finite? Yes, A is finite, so for each point in A, I have one set. So does the union of G sub x's when x is in A, does this contain A? Yes, for each x in A, well, there is G sub x which contains that. So this is a finite subcovering of script G for A. But then this means that A is compact with respect to tau. So if I take any topological space and any finite set in that space, that will be compact with respect to the topology in question. So compactness is really an extension of finiteness. Okay, any questions here? No. Now, let us then consider the two extreme cases. X non-empty set, tau 1, what do you think about subsets of cap X, about their compactness with respect to this indiscrete topology? Well, here, the set of all open sets is finite. Thus, there are just three possible collections of open sets. Well, singleton, the empty set, singleton cap X, and this itself, but they're all finite. So if something covers some set, then it is a finite subcovering of itself for that set. So every set in here is compact. Check that. Every subset cap A of X is compact with respect to tau 1. So that's one extreme. What do we expect when we consider the other extreme, that is the discrete topology? Well, something at the opposite end should happen. But we know, well, the absolute opposite would be that nothing is compact. Here everything is compact, but nothing is compact. That's not possible because all finite sets are compact. So, well, we'll see that when we consider the discrete topology, in that case, a set will be compact if and only if it is finite. So it will get reduced to the minimal set of compact sets. But we'll continue next hour.